Jain to all. Today I am here to present the fifth video lecture of the series Digital Signal Processing, so BEC 503, and the topic of my today's lecture is Decimation by Factor D in Multirate Signal Processing. I am Dr. Amit Garg, Associate Professor in EC Department of Akgec. So let us start with the presentation. So first of all, we will understand that what do we mean by the multi-rate digital signal processing. In many practical applications of DFC, one is faced with the problem of changing the sampling rate of a signal, either increasing it or decreasing price or not. Means as we will discuss about the applications of DFC, we will see that sometimes we require that a single signal to be sampled at different rates. For that case, we require this multi-rate signal processing. So the process of converting a signal from a given rate to a different rate is called sampling rate conversion. So simply sampling rate conversion is the process in which we will try to change, or we will change the sampling rate of a given signal, and it is called sampling rate conversion basically. Internal systems that employ multiple sampling rates in the process of digital signals are called multi-rate digital signal processing systems. Means there are two types of systems. One is single rate systems. Another one is multi-rate systems. So in the case of multi-rate systems, these systems allow multiple sampling rates. Okay, so that's why it employs multiple sampling rates in the processing of digital signals. As we are discussing that discrete time systems may be single rate systems or multi-rate systems. The systems that use single sampling rate from A to D converter to a D to A converter are known as single rate systems, and the discrete time systems that process digital data at more than one sampling rate are known as multi-rate systems. Okay. So now how we will achieve this? How we will change the rate? So the rate can be changed with the help of upsampler and downsampler. You know, this upsampler and downsampler are the devices. With the help of that, we can change the sampling rate of the given signal. So the basic operations in multi-rate processing is to achieve this are decimation and interpolation. So there are basically two types of operation. One is decimation, another one is interpolation. So if we want to change the rate of signal, if we want to change the sampling rate from a given rate to lesser rate, then that process is called decimation. Means if we want to reduce the sampling rate, then the process is called decimation, and if you want to increase the sampling rate, then the process is called interpolation. So decimation is for reducing the sampling rate and interpolation is for increasing the sampling rate. So if you are reducing the sampling rate, then these factors, let's say this factor will denote by D. Decimation factor is denoted by D and interpolation factor is denoted by I. Generally, it is represented by D and it is represented by I. Otherwise, there are some conventions also. Also like M is also used for this. So now, in this particular lecture, I will focus more on decimation part. So decimation is reducing the sampling rate of a discrete time signal is called downsampling. So the sampling rate of discrete time signal can be reduced by a factor D by taking every dth value of the signal. So this you can see in this particular figure. This is the figure of a downsampler, and it is downsampled by a factor of D. So if we are, let us suppose we are having a signal which is signal xn, which is having, let's say, rate fx, then after downsampler the rate will be reduced by a factor of D. So the signal yn will become having rate, let's say fy, then fy will become fx by D. It means rate will be reduced at the output. And in time domain, if we want to represent it like if the input signal is xn, then output signal is yn equals to x times dn, where d is nothing but any integer value that may be greater than 1. Let us suppose 2, 3, like this. Okay. So you can see here is a signal xn which is represented by this series 1, 2, 3, 1, 2, 3, 1, 2, 3, like this. Then if you want to calculate the value of x2n, where d is equal to 2. So if we are taking D is equal to 2, then you can see that after 1 you will get 3, then again 2, then 1, then 3. It means when D equals to 2, what we have to do, basically we have to remove one sample between the existing samples, between the adjacent samples. So you can see after 1 we will take 3, after that we will take 2, and like this. And when we are calculating x3n, it means D equals to 3. So when D equals to 3, it means we will reduce the 2 samples, means D minus 1 samples. In both the cases you can see D minus 1 samples to be removed from the input signal, to be removed from input signal. So you can see x2n is obtained by keeping every second sample of xn, and x3n is obtained by keeping every third sample of the xn and removing other samples. So this is how downsampler works. So now what is the difference between downsampler and a decimator? So you can see this downsampler is simply change your sampling rate from a given rate to reduce by a factor of D. But what are the basically issues if we will directly downsample our signal? We can do it, but this will lead to aliasing effect. So what is the process that will be followed in decimator to reduce the sampling rate but to avoid aliasing? So decimation is the process of decreasing the sampling rate by an integer factor D by keeping every DS sample and removing D minus 1 samples in between samples. So this is the graphical representation. We can see here this is x2n, this is basically x3n. So this is the same, you can say this is this figure is basically the representation of these signals in graphical form. Okay. So now how we will do it? So decimation by a factor D. So let us assume that the signal xn with the spectrum x omega is to be downsampled by an integer factor D. So we are taking a signal xn, means continuous time signal xn, and if we draw its spectrum, it is you can say is like x omega, and the spectrum x omega is to be assumed to be non-zero in the frequency interval 0 to pi, or equivalently mod f is less than fx by 2. So simply what happened, you can say the signal xn which we are taking is basically a bandwidth, a band limited signal, and we want to downsample this band limited signal. We know that if we reduce the sampling rate simply by selecting every dth value of xn, the resulting signal will be an aliased version of xn with a folding frequency of fx by 2t. Okay, so what we will do, if we will take a signal and if we will do directly downsample this signal, then what happened? It will lead to an aliasing effect. So to avoid aliasing, we must first reduce the bandwidth of xn to f max equals to fx by 2d, or equivalently to omega max equals to pi by d. So in simple words, you can predict from here, like in the process of decimation, what happened? In the process of decimation, what happened? Signal compressed in time domain, so it will expand in frequency domain. So if it will expand in frequency domain, then in that case aliasing effect occurs. So how you can remove this, or how can you neglect this aliasing effect? By compressing the signal first and then do the downsampling. So what happened? The expansion occur in the process of decimation in the spectrum will now be adjusted against the initial downsampling of the signal. Okay, so to avoid aliasing, we must first reduce the bandwidth of xn to f max equals to fx by 2d, or equivalently omega x equals to pi by d. So what happened when you will do the later on when you will do the downsampling for this signal pi by d, then expansion occur, and this x omega will now become from pi by d into d. It means from minus pi to pi. So then we downsample d and thus avoid aliasing. This aliasing problem can be eliminated by band limiting the input signal by inserting a low pass filter called anti-aliasing filter before the downsampler. So what we have to do, we know that our signal after decimation, our spectrum is going to be expand. So what we will do? Initially, for compensating it, what we are doing? We are decreasing the bandwidth of our input signal in time domain. And so how we will do it? We can do it by passing the signal xn through a through a low pass filter, which will restrict the bandwidth of the input signal from input signal from minus pi to minus pi to pi to minus pi by d to pi by d. The anti-aliasing filter and the downsampler together is called decimator. So now what we have to do? We have a signal xn. So first of all, we have to pass this signal xn through our low pass filter. Why? Because we want to restrict its bandwidth. So let's say bandwidth is signal is band limited. So signal is from minus pi to pi, you can say. So after low pass filter, you are having a signal which is from minus pi by d to pi by d bandwidth. Okay, so it means the cutoff frequency of this low pass filter is from minus pi by d to pi by d. Okay, and once you are having a signal xn after passing this through a low pass filter with reduced bandwidth, when we will pass it through a downsampler, then the signal yn that you will obtain at the output is basically having sampling rate which is equal to, let's say it is fx, then this is equal to fx by d simply. This is simply fx by d. And in the process of decimation, this bandwidth expansion occurs, so that the bandwidth here is again from minus pi to pi. Okay. So this we can see through a block diagram which is showing here. So first of all, we will pass our input signal xn through a decimation filter. It is also called anti-aliasing filter, and this is a type of low pass filter. And the output of this decimation filter is then passed through a downsampler to get the output signal. So you can see here, let's say input signal is having rate fx, which is equal to 1 by tx, and after downsampling, after passing through a decimation filter, only bandwidth will be restricted, but there will be no change in the rate. But when this Vn signal will pass through a downsampler, the rate will again change. So this is the decimation process. We can see in this figure. The input sequence xn is passed through a low pass filter characterized by the impulse response hn and a frequency response hd omega, which ideally satisfies the condition. So now we are assuming that this low pass filter which we are using in the process of decimation is an ideal low pass filter, then its frequency response must be represented by this hd omega should be equal to 1 between minus pi by d to pi by d, or 0 otherwise. So thus the filter, now we are having this input signal xn where bandwidth is from minus pi to pi, and this is the low pass filter which is having cutoff frequency between minus pi by d to pi by d. So what happened when you will pass it? We are having a signal with frequency minus pi by d to pi by d. So thus the filter eliminates the spectrum of the x omega in the range minus pi to minus pi by minus pi to minus pi by d and pi by d to pi, because this mod omega sign is here. So of course the implication is that only the frequency components of xn in the range mod omega less than pi by d are of interest in further processing of the signal. Okay. So you can see this diagram. So what is this Vn? So this is a linear filtering operation. You can see xn is the input here and hn is the impulse response of the filter. So that Vn is basically the output of this low pass filter, and this stands out to be the convolution operation between xn and hn. So Vn will become, Vn is basically xn convolution hn. Okay. So this is basically the convolution sign. I am drawing like this. So Vn will become now xn convolution hn, which you can write summation k equals to 0 to infinity hk into x of n minus k, which is then downsampled by factor d to produce ym. So what is the relationship between yn and vn? Because you are downsampling, so ym equals to v times md. So y or you can write yn equals to v times nd. We are just changing the index n by m. So ym equals to vmd. Now we can put n equals to md here to get this equation. So this will become hk into x of n is equal to md. So h of k x of md minus k means the output ym will comes out from this equation hk into x of md minus k. Although the filtering operation of xn is linear, you can see here this operation is linear operation and time invariant, linear time invariant operation. But what happened? This operation, the downsampling operation, is combination with the filtering results in a time variant system because of this downsampling operation. Okay. So consequently, the overall linear operation on xn is not time. Linear filtering followed by downsampling on xn is not time invariant. Means the overall operation is linear, but it will not become time invariant because of this downsampling operation. Okay. Now the frequency domain characteristic of output sequence ym can be obtained by relating the spectrum of yn to the spectrum of the input sequence xn. So now for deriving this, let us assume that a sequence v cap n is equal to vn when n equals to 0 plus minus d plus minus 2d. You can see these d values are basically integer values. So you are having v tilde n available only at values of vn where n is a multiple of d. So vn is a spectrum of a sequence obtained by multiplying vn with a periodic train of impulses pn with period d. So this v tilde n can be viewed. We can view this. It is like how we have obtained it. We have obtained it by multiplying vn with a periodic train of impulses where impulses basically are located at multiple of d. Okay, so we can represent its discrete Fourier series representation. So which can be represented by Pn equals to 1 upon d summation k equals to 0 to d minus 1 e to the power j 2 pi kn by d. Now v tilde n is basically Vn into Pn, where Pn is basically this, which we have already discussed. Okay, so from here ym is equal to, you will see v tilde md, and v tilde md is basically put n equals to md here. So it is vmd into pmd and it is equal to pmd. Okay, oh sorry, equals to vmd. Now if you will see the Z transform of the output signal ym, so it is yz equals to summation m equals to minus infinity to infinity ym into z to the power minus m. Now ym is similarly ym is nothing but v tilde md into z to the power minus m. And now put md equals to m. If you will put md equals to m, so this md will become m and this m will become m by d. So this is basically the output Z transform of the output signal. Now again we will take it summation m equals to minus infinity to infinity vm into z to the power minus m by 2 and m by d. So v tilde m is basically this summation m equals to minus infinity to vm, and you can see z to the power minus m by d will comes like this, and v tilde m is basically vm into pm, and pn put n equals to m here. So pm is 1 by d summation k equals to 0 to d minus 1 e to the power j 2 pi k m by d. Okay, now 1 by d you can take outside, k equals to 0 to d minus 1 you can take outside, and then it will become vm into this expression. You can write like e to the power minus j 2 pi k by d, 1 m power m e to the power m is comes over here, and you can write 1 by d like this, and you can make overall power minus m. Okay, now this is summation m equals to minus infinity to infinity vm into z to the power minus m, but in place of z this term will become this. So when vm into z to the power minus m is, then we can write it like vz, where z is this. So we can write it like v e to the power minus j 2 pi by k by d into z to the power 1 by d. Now Now according to this, now we will see the block diagram. If we will see this frequency, we will see this is in frequency domain. Then what is the value of Vz? Vz is, if you will see here, this Vz, if you will see this particular block, Z transform of this Xn is Xz, Hn is Hz, and Vn is Vz. So now Vz is simply the multiplication of Xz into Hz. So this we have written over here. Vz is equal to Hz into Xz, because we are using subscript d, so that's why it is Hd e to the power minus j 2 pi k by d into z to the power 1 by d into x e to the power minus j 2 pi k by d into z to the power 1 by d, because we know that Vz equals to Hz into Hz. Now, because we want to because we are interested in finding out the spectrum of the output signal, and this is the Z transform. Now, because we are using a discrete time signal, so what is the relationship between Z transform and spectrum? So how you get the spectrum? If you will simply calculate the DTFT, then you will get the spectrum. So how you will get it? Because you know Z equals to R e to the power j omega, but in this case R is equal to 1. R equals to 1. So DTFT is nothing but the Z transform evaluated over unit circle. Okay, so if we are interested in, then we will put Z equals to e to the power j omega simply. So this will become y e to the power j omega, and how we are getting, if you will put Z equals to e to the power j omega. So this we can see from here, because the rate of the output signal is now y, so we are writing y omega y, and 1 by d summation 1 by d summation k equals to 0 to d minus 0 to d minus 1 hd e to the power minus j 2 pi k by d. In place z, you will write e to the power j omega in both the places, and then you will take common. So this will become hdz e to the power j omega by d. So when you are taking common e to the power 1 by d, then it will become omega minus 2 pi k. So you can say this is omega y minus 2 pi k by d. And similarly like here, and this is basically the notation. Actually this is simply the notation, that's why we are writing it not in terms of e to the power minus. Otherwise it should be written like e to the power minus, but here we are representing it in terms of basically notation. That's why hd wy minus 2 pi k by d into x wy minus 2 pi k by d. But if you want to basically how aliasing occurs due to these k values. So if we will properly design a filter hd omega, the aliasing is eliminated, and consequently, so what we will do, this k is equal to 0, so this will become 1 by d hd omega y by d into x wy by d. And because this, for a properly designed filter, the frequency response value will become 1, so wy equals to 1 by d x wy by d. So now if you want to see the spectra of input, output and other signals, we can see here. This is basically our band limited signal. You can see the value is from minus pi to pi. Frequency rate is omega x, and mod of x omega x. Basically we are plotting the magnitude over here. Then we are passing it through a low pass filter. The bandwidth of this low pass filter is minus pi by d to pi by d, or you can say the cutoff frequencies are from minus pi by 2 pi by d. Magnitude is 1 because it is an ideal low pass filter. Then so that we will get, this is the output. You can see this is the output. Then this is the intermediate signal after passing through low pass filter. You can see now the output will become minus pi by d to pi by d. So you can see our input signal has bandwidth now from minus pi by d to pi by d, but we can see rate is not changed yet. You can see rate is not changed yet. Then in the final step we will do the downsampling. When we will do the downsampling, then this spectrum will expand in frequency domain, then these values will become now minus pi to pi. So this is basically for input signal, this is for low pass filter, this is the product of input signal and low pass filter, and this is basically the output of downsampled output which we want after decimation. So similarly frequencies will be changed accordingly. So basically we can see this is basically next is aliasing effect and anti-aliasing filter. We can find that the spectrum obtained after, so this is figure 5, downsample will overlap if the original spectrum is not band limited to pi by d. This we have already seen. This overlapping of spectra is called aliasing. Therefore, aliasing due to downsampling a signal by a factor of d is absent if and only if the signal xn is band limited to plus minus pi by d. So if the signal xn is not band limited to plus minus pi by d, then a low pass filter with a cutoff frequency pi by d is used prior to downsampling. This we have already done. This low pass filter which is connected before the downsampler to prevent the effect of aliasing by band limiting the input signal is called the anti-aliasing filter. This is basically the anti-aliasing process. This is the process of aliasing. So what happened? We are considering if we are passing it through a low pass filter initially, then this aliasing filter will not be present. So these are the references that I have taken for making this presentation. Thank you. Thank you so much.